Okay, for our next segment, we start with the ideal gas law. The ideal gas law is what you get when you take the combined information from all of those trends that we just discussed, relationships between properties as they change, and you put them together into an equation that you can use to find the properties of a sample of gas when nothing is changing. And this is actually quite useful because a lot of times you've just got a sample of gas and you're not really doing anything to it. You just want to know something about it. There's something about it that you don't know, and you want to be able to figure that out from what you do know about it. And the ideal gas law is usually written in the form PV equals nRT. That is, for any given sample of gas, its pressure times its volume will be equal to the number of moles in the sample times a constant, which we'll get to in a moment, times its temperature in kelvins. And that works out for any sample of any gas under reasonable conditions. It's called the ideal gas law because in order to use this equation, you technically need a gas that's exhibiting what's known as ideal behavior. And ideal behavior has to do, well, it's kind of a circular definition. An ideal gas is one that obeys the ideal gas law. Yeah, okay, that helps a lot. But actually, an ideal gas is one that obeys the tenets of the kinetic molecular theory of gases, which we will get to a little later. So we're not really going to get to that yet. But suffice it to say at the moment that under most circumstances within reason, most gases behave ideally or close enough to ideally that you can use the ideal gas law without much error. Some of the assumptions for the ideal gas law are, like the assumptions, like I said, of the kinetic molecular theory of gases. They include the sense that one of the tenets of the kinetic molecular theory of gases is that gas particles have no volume at all. And of course, that's not true. But in practice, as long as the particles are far apart from each other relative to their own volume, then the ideal gas law is close enough. And in practice, under almost all circumstances, gas particles really are far apart from each other relative to their own sizes. So you can usually use the ideal gas law. Another tenet of the kinetic molecular theory of gases is that gas particles have no attraction for each other. And generally that's true because gas particles are far apart from each other and they're moving around at a high rate of speed. And so they're too far apart to develop any kind of attraction for each other, and they're moving too fast to develop any kind of attraction for each other. When those conditions are not met, when the particles are close to each other, and when they're moving slowly, that's when the ideal gas law starts to fail. But again, those are pretty extreme conditions you need in order to make that happen. So under most conditions, again, the ideal gas law is either valid or close enough that you can use it without much error. In this equation, P stands for pressure, and because you've only got one pressure and one volume and one temperature, the units do matter in the ideal gas law, unlike the Boyle's law and Charles' law, where units for temperature were the only things that mattered. Units for everything will matter in the ideal gas law. That's partly because of this R, known as the universal gas constant. That is a proportionality constant, and it's got a number, 0.082057, which helps relate the numbers to each other in the equation. But it also has units, and those units are liters times atmospheres over moles times Kelvin. And those units in the constant R dictate the units that have to be used in everything else in this equation so that the units for your answer will work out correctly. So for pressure, the units do have to be in atmospheres so that they can cancel out with the atmospheres in the constant R. Volume has to be in liters so that they can cancel out with these liters. N is number of moles, so that shouldn't be a problem. Temperature does have to be in kelvins, so it can cancel with that kelvins there. So the units for everything matter. If you're given the units in the, if you're given a quantity in the wrong units, you're going to have to change them into the correct units before putting them in the equation. If you look at this equation, PV equals nRT, it's not actually used in this form very often because, how often are you looking for pressure times volume or number of moles times R times temperature? You're usually looking for just one of these things. And so you can rearrange the equation to find pressure just by dividing both sides by V. So P is nRT over V. You can solve for V by dividing by P. So volume is nRT over P. And N is PV over RT. And temperature would be PV over NR. Okay, so generally you'll be using one of these four forms here when you're actually using this gas law in problems. To look at some examples of what you can do with this, we could look at what pressure is there in a car tire. With a volume of 8.50 liters, which contains 0.552 moles of gas at 305 K. Well, if you're looking for pressure, that's going to be nRT over V. N is moles of gas, that's 0.552 moles. R, 0.082057 liters, atmospheres over moles, kelvins. And T is 305 kelvins. And all of that is over the volume is 8.50 liters. When you look at the units, you notice that moles here will cancel with that moles in the R constant, and kelvins cancel with kelvins in the denominator of the units for R. And let's see, liters will cancel with liters in the R constant, and that leaves us with units of atmospheres. And that's good because that's a pressure unit. And when we work this out, no, sorry, it's 1.63 atmospheres. If we wanted this in since car tire pressures are usually measured in pounds per square inch, we could change this to pounds per square inch just by taking the number of atmospheres and multiplying by the fact that there's 14.7 psi for every 1 atmosphere. And then we would end up with, yes, 23.96 psi. Okay, we can also look at, say, what volume would be occupied by 0.556 moles of gas at pressure of 715 millimeters of mercury and 58 degrees Celsius. Well, here we have V is nRT over P, but before we can put these numbers in, we need to do some conversions. N was given as 0.556 moles, and number of moles is what we want for N, so that's good so far. But the temperature was given as 58 degrees Celsius, and we need that in kelvins. So 58 plus 273 is 331 kelvins. And the pressure was in millimeters of mercury. We need that in atmospheres. So you divide by 760 and you get 0.941 atmospheres. And those are the numbers you have to put into the equation. So we get 0.556 moles times R times R times T all over P. If you note that moles will cancel with moles in the units of R, and kelvins likewise cancel with kelvins in the units of R, and atmospheres will cancel with atmospheres in the units of R, leaving us with liters as the units for the answer, and that's a volume unit, and that's what we wanted. So far so good. And we got 16 liters, 16.0 liters. And we can also look at finding pressure. So what would be the pressure in millimeters of mercury of 0.133 grams of helium in a volume of 648 milliliters at a temperature of 32 degrees Celsius? They didn't give us anything in the right units here. All right. Pressure is nRT over V. N is number of moles. Notice that they gave us a mass of helium. So to find number of moles of helium, we have to go to the periodic table and find the molar mass of helium, which is 4 grams per mole, or 1 mole for every 4 grams of helium. And so 0.133 divided by 4 will be 0.03325 moles of helium. Temperature is 32 degrees Celsius, but that's plus 273 because we need it in kelvins, and that's 305 Kelvin. And volume is 648 milliliters, but we need it in liters, so there's 1 liter for every 1,000 milliliters. and that's 0.648 liters. Okay, so finally we can put the numbers in. 0.03325 moles times R, 0.082057 liter atmospheres over mole times Kelvin, and temperature 305 kelvins, all over 0.648 liters. So moles cancel with moles, kelvins cancel with kelvins, liters cancel with liters, leaving us with atmospheres. And that's 1.28 atmospheres. But it said millimeters of mercury in the question. So we have to take the atmospheres and multiply them by the number of millimeters in an atmosphere, and that's 760. And we end up with 976 millimeters of mercury. Okay. So next up, we have applications of the ideal gas law. There are several things that you can actually use the ideal gas law to establish. And then once it's known, you can just kind of use that fact without having to derive it over and over again. One of those things is molar volume. And molar volume just means the volume of one mole. And so the molar volume of a given gas will just be how much volume does 1 mole of that gas occupy at a given temperature and pressure. But of course, since gases all behave the same with respect to temperature and pressure and volume and number of moles, it doesn't matter what the gas is. The molar volume for any gas will be the same at a given temperature and pressure. And that kind of makes sense if you think about the ideal gas law. Nowhere in the ideal gas law is there anything that pertains to any specific gas. There's no place in the ideal gas law for things like molar mass or any particular density or anything like that. All gases behave the same with respect to everything that's in the ideal gas law. So the molar volume of a gas, in other words, it depends on the temperature and the pressure, but not on what the gas is. We have a particular temperature and pressure that are known as standard temperature and pressure. Abbreviated STP. And that it would be 0 degrees Celsius or 273 Kelvin and 1 atmosphere of pressure. So the molar volume of any gas at STP is 22.4 liters. And there are some gases that are a little bit different from that, but a vast majority of them round off to 22.4 liters. And you can calculate this from the ideal gas law. And we can try it right now. So what is the volume of 1 mole of a gas at 0 degrees Celsius or 273 Kelvin and 1 atmosphere pressure? And the volume comes out to be, let's see, 1 times 0.082057 times 273, 22.401561. But to keep it reasonable for significant figures, actually, that's an exact number. 273 was 3. I'll count that as 3. So 22.4. So there you go. That is derived from the ideal gas law. But now that we know that number, you don't have to go back to the ideal gas law every time you need it, because a lot of questions are asked for conditions of standard temperature and pressure. So if you see STP or 0 Celsius and 1 atmosphere in a problem, you know that 1 mole of gas occupies 22.4 liters, and you don't have to go back and calculate it. You can calculate the molar volumes at other temperatures and pressures from the ideal gas law also. And since we saw how to do it at standard temperature and pressure, you can just put other values in as needed and figure out what the molar value is at, the molar volume value is at those temperatures and pressures as you need to. Another thing that you can find from the ideal gas law is the density of a gas. The density of a gas does change from one gas to another, and it also changes with things like temperature and pressure. And you can actually, like I said, you can use the ideal gas law to figure out what the density of a gas is at any given temperature and pressure. Actually, if you know the molar volume of a gas under the given conditions, you can find the density quite easily. Because the density is just mass divided by volume. So assuming you know what the gas is, you can go to the periodic table and find the mass of a mole of that gas, which is just the molar mass. Divided by its molar volume, which we know at STP is 22.4 for any gas. And at other conditions, you can just slip those conditions into the ideal gas law and find out what the molar volume is under those conditions. And that gives it in units of grams per liter. And so at STP, the density of a gas would just be its molar mass divided by 22.4. And as it turns out, the density is directly proportional to molar mass. That's because, at any given temperature and pressure, all gases will end up having the same molar volume. And so effectively at a given temperature and pressure, the molar volume is a constant no matter what the gas is. It's only the molar mass that's changing. And the changes in the molar mass are the only thing that could have an effect on the density. So density will be directly proportional to molar mass. If you've got two gases and say helium and hydrogen, helium is twice as heavy as hydrogen. It has a molar mass of 4 grams per mole, whereas hydrogen only has a molar mass of 2 grams per mole. The helium will be twice as dense as the hydrogen. Okay, so gases that have molar masses that are less than the weighted average of the gases that are found in air, which is mostly a combination of nitrogen and oxygen. And so the weighted average of nitrogen and oxygen in the air is about 29 grams per mole. Any gas with a molar mass less than that will tend to rise in air because it will have lower density. They'll keep rising in air until they reach a point where the density of the air around them is the same as their density. And then they will tend to stay there. And as advertised, you can also use the ideal gas law to find the density of a gas. We know that the ideal gas law is usually written as PV over equals nRT. Well, if you rearrange that a little bit, you end up with N over V equals P over RT. N over V has units of moles per liter. And it's commonly known as molar density. So molar density is P over RT. You can get density in more conventional units. Like grams per liter, because if you take N over V equals P over RT, and that's molar density in terms of moles per liter, then you can take molar density times molar mass. And if you look at the units, molar density, of course, is moles per liter. And molar mass would be grams per mole. And you'll notice that moles cancel. And you end up with grams per liter. So if you want grams per liter, all you have to do is take molar density times the molar mass, and you've got grams per liter. Or you could just rearrange the equation a little bit. So that you have density is equal to pressure times molar mass over RT. And you'll notice that density is proportional to molar mass. And it's also proportional to 1 over the temperature. Because, of course, things expand, especially gases, when they heat up. And when they expand, things get further apart. And getting further apart means that the density is lower. Okay, so there are a couple of examples that we can do for calculating the densities. Calculate the density of xenon at a pressure of 742 millimeters of mercury and a temperature of 45 degrees Celsius. So density is pressure times molar mass over RT. Got to remember, though, this equation is derived from the ideal gas law. So all of the units have to be the same as they are in the ideal gas law. So pressure has to be in atmospheres. So you take 742 divided by 760, and you end up with 0.976 atmospheres. Temperature is going to be 45 plus 273 equals 318 Kelvin. And the molar mass of xenon from the periodic table is 131.3 grams per mole. So pressure is going to be 0.976 atmospheres, molar mass 131.3 grams per mole. R is 0.082057 liter atmospheres per mole Kelvin times temperature, which is 318 Kelvin. So now if you look at these units, atmospheres cancels with atmospheres, kelvins cancel with kelvins, moles cancels with moles, and you get grams per liter. And the number would be 4.91 grams per liter. And something else you could do with this would be, say, a gas has a known density. And you want to know its molar mass. So say you've got a gas that has a density of 1.43 grams per liter at a temperature of 23 degrees Celsius and a pressure of 0.789 atmospheres. First of all, you got to make sure that the temperature is in Kelvin. And I never actually said that we were looking for the molar mass, so that is what we're looking for. So if D equals P times MM over RT, you rearrange it for MM, you get DRT over P. So we've got density is 1.43 grams per liter. R is 0.082057 liter atmospheres over mole Kelvin times T, which is 296 K, over 0.789 atmospheres. And if we look here, we've got atmospheres will cancel with atmospheres, kelvins cancel with kelvins, liters cancel with liters, and we get grams per mole. And so grams per mole, it'll be 44 grams per mole. Most likely carbon dioxide. So one more thing that you can do with the ideal gas law. All right, it's about time to end this particular lecture, but I'll be back for the next one before long.